all in these different categories. And because your textbook really leaves this as an exercise, I want to work out the halting problem. In other words, is it decidable whether a given Turing machine M halts on an input W? This is a very practical problem to consider if you think about all the times you've ever halts on an input. If you think of all the times that you've ever started running a test case and thought to yourself, this test case has been running for a long time. Is this program actually going to give me an answer? Or is it time to hit Control-C and kill the thing? Okay. With all the various tools, from compilers to analysis tools and things like that we have available to us, that might be the kind of thing you would hope that somebody could write an automated tool for. And that's essentially what this question addresses. Is it possible for someone to ever put together an algorithm that would determine whether some procedure halts on a particular input or not? Should we keep it running and wait for the input, or is it time to, should we give up? Now, the way we're going to handle this is we're going to turn this into a language problem. And the way we'll do that is we'll consider the language LH as the set of all strings of the form M sub I 111 W sub I such that M sub I halts on the input W sub I. And what we really want to know is there a Turing machine that will give us yes or no answers, halting all the time? So will it actually give us yes or no answers without making us wait forever to the question, does this Turing machine halt on this input? And be able to do that for all Turing machines. So, how do we check this out? The answer, I will tell you right away, is no. This is not recursive. But let's assume, by way of contradiction, that we have a Turing machine M that can decide the LH membership. Okay, so by decide, I mean the same thing I did when I said that those regular languages are decidable languages. I mean that this has to give us a yes or no answer, accept or reject, and it can't go into an infinite loop doing so. So let's assume that there actually is a Turing machine somewhere that can actually solve this problem. Now, let me, as a creative and sometimes nasty programmer, define a new Turing machine, and rather than give the full details of this, I'm going to sort of write out what I want this Turing machine to do in pseudocode. So this Turing machine, given an input X, which will be a string of zeros and ones, should apply our Turing machine that we just said exists and always halts, M of X, that determines whether X is in L sub H. And if So it runs that machine, and if it accepts, M prime will go into an infinite loop. Else, that is, if M of x rejects, halt and accept. So in a sense, you can almost see that what I'm doing is I'm perversely setting something up to do exactly the opposite of what our hypothetical halting decision machine tells us. If the machine says that, X describes a Turing machine that halts, we're going to go into an infinite loop. If it says that it describes a machine that goes into an infinite loop, we're going to halt. So what we're going to do with that then is say, look, if we have this machine, M prime, there's got to be some one of these W sub i's that represents its encoding. So let W of that M prime machine, and then let's run M on W, 111, W. And let's consider what the possibilities are. So one possibility, when we run it on this, remember that what M does, I want to run this through M prime, our new machine. So we run this M prime on its own encoding, looking at itself as input. So if our M sub x, which is used to looking at a Turing machine, 111, and an input, so this looks perfectly fine as an input to our machine for deciding whether Turing machines halt. That's the form in which it should get. It's just that we're feeding this Turing machine itself as an input, which is a very common trick in these kinds of problems. So one possibility if M halts on that input, accepting, what does that mean? It means that M tells us that M prime halts on that input. Right? Because that's what M does, is it tells us whether the machine that we've given it will halt on the input we've given it. So if it accepts, then M is telling us that M prime halts, except that if M of x accepts, look what we do. We go into an infinite loop. And that's a contradiction, because we are saying that, in fact, our M that decides whether a Turing machine halts says, yes, this halts, and then we perversely go into an infinite loop just because it said that. Of course, the other possibility is that if M sub I halts but rejects that machine, well, then our definition says that that means M prime goes into an infinite loop. It doesn't halt. But look what we do in that case. We halt and accept. And so doesn't actually matter what M tells us. we get a contradiction either way. If M says that M prime halts, M prime goes into an infinite loop. If M says that M prime goes into an infinite loop, then M prime halts. We got a contradiction either way, which means that our assumption up at the top that we actually have a Turing machine that can decide the membership of the halting problem has to be false. Can't happen. So that tells us that, in fact, this is not a recursive problem. It's not a decidable problem. It is not decidable whether this machine halts. Is it recursively enumerable? Yes, as it happens, the very existence of the Turing machine proves that it's recursively enumerable. If you've got a Turing machine, you can enumerate all of the inputs that it would eventually accept. But it's not decidable. So there's no help for us when we're running that test that's running slow. No automated tool is ever going to be able to tell us if it's time to hit the cancel button or not.